Hey guys, welcome back to my YouTube channel. So here we are going to implement a full adder using a 3-state decoder. So I hope you guys have tried as a homework. So I hope I can see some of the responses. It will be good to see some things. If you guys have tried, please post in the comment section so that I will know that you guys are on the same track. Okay. So take the case that. So this is what the decoder that we have. So this is enable input. This is 3:8 decoder that we have. So three input that we are having. So that is A, B, C. Okay. So we are going to implement full adder, right? So we know S, which is equal to summation of min term, which is equal to 1, 2, 4, 7. The carry Cy, which is equal to summation of M, 3, 5, 6, 7. So in decoder, we can clearly note that the function, if any one of these one values is represented, then the function will be need to be 1. So here the 0, which is nothing, which is eliminated. 1, 2, 3, 4. So 0, 1, 2, 3, 4, 5, 6 and 7. So 5, 6 and 7. So just this is a summation of get thing, right? So let's add all the things. So 1, 2, 4 and 7. So let's add all this to an OR gate. So if even any of this min term is 1, then output will be 1. So that is the summation sum. So for carry, let's add all the things. Let me take another one color. So 3, 5, 6 and 7. Okay. So let's add all together. And if any of the one is out, then carry will be there. So this is how this thing can be done with multiple decoder. So I can clearly state in the previous one, even if any of the thing is resembling, like even if any of the enabled is enabled output, and based on the thing, the output will be respond. So any one will be enabled. So if the input is given as 3, so for an example, if input is given as 0, 0, 1 or 1, 0, 0, then 1 will be triggered, then we will be able to get the sum here. So that is how we can implement the full adder or off adder, any kind of logic in the decoder. So this one, please make a note of it. So I hope this is understood for you guys. So now from here we can conclude all our discussion on the decoders. So let's get into encoders. So encoder is also same thing, but the opposite version of decoders. So let me give you some example. So let's take a 3:8 decoder encoder. So let me draw a truth table. So this is for En. This is for 8 inputs. This is for output y0, y1, that thing. Okay. So let me also draw a encoder. Okay. So this is I7, I6, I5, I4, I3, I2, I1, I0. So I7, I6, I5, I4, I3, I2, I1, I0. So this is 8:3 normal decoder. So there is some priority decoder is also there. Priority encoder is also there. I will let you know that in next. So this is enable. So here it is output Y. So there is 3 input, right? So this is Y0, Y1, Y2. So this is enable. So if enable is 0, whatever may be the condition, that will be skipped. So that we can take into account. So let me write all the 7 inputs. I7, I6, I5, I4, I3, I2, I1, I0. So here it is Y2, Y1, Y0. I'm taking this as MSB. So even if any of the case, this bit will be considered as X. No, don't care only. So output will be 0, 0, 0. So this is 1, 1, 1, 4, 5, 6, 7, 8. So 0, 0, 0, 0, 0, 0, 1. Then output will be 1. So here if you see, this is converting from a lengthier binary to normal decimal. So that's why we will sometimes call as a code converter. So here 8-bit is converted to 3-bit. So here we can consider as a octal to binary converter. So like this way we can name it. So that's why we will be calling this as a code converter. So this will not be resembling to you guys. If you guys take 1 is to like 2 is to 1 decoder encoder, there you can clearly see the code conversion that is happening. So the same thing here, it is 0 0 0 0 0 1 0. Then here we can represent that as a 0 1 0. Okay, so similarly if it is 0 0 0 1 0 0, then we will be 1 1. Okay, so similarly we can fill entire table. So let me complete all the one. This is 4, this is 5, so this is 1 0 1, so 0 0, so this is 1, right? So this can be written as 1 1 0. I think this is 6 1 0 1, right? So 1 2 3 4 5 6 7. So this is the last one. 1 2 3, this is 1 0. So I missed one thing. So here it will start from 0. So this is 0. Okay, as it is 0, I0 is 0 only, right? So 0 0 1 0 1 0 0 1 1. Here it is 1 0 0 1 0 1. Okay, sorry for that one. So here it will be 1 1 0. So 1 0 0 0 0 0 1 1 1. So this is how this truth table will look like. This is normal encoder. There is no difference in this. So here we can take all the ones. So for an example, how the y0 can be written as y0 can be written as where are this 1. So this is I1. So y0 which is equal to I1 plus I3 plus I5 plus I7. So like this way we can write, because in that other case the output is 1. So from here we are mimicking is. So here even if any of the one is here, any of the one is 1, then output y0 will be enabled. Okay, so this is the normal thing. So this is one thing. So here some kind of thing, if more than one input or one at a time in a normal encoder, this can't work, because we can overcome because if a more input is coming, then all the things will be enabled and we may not know which exact number is coming there. So what is the exact thing that is coming, so that we may not know. For an example, if this is also enabled and this is also enabled, then the output will be confused. So which in to take? So instead of 0, if any of the bit, if a two more than one bit is set there, then we will be landing in a problem. So in order to solve that, we are getting into a thing that is called priority encoder. So I'm just changing the same thing here. So it will reduce a huge time in writing, right? So that's why I'm changing the thing. So we are converting this into priority encoder. So what are the changes will come in the priority encoder is that, so when this condition, when the higher bit is set to 1, all the below bit, even if it is 1 or 0 or anything, then the output will be remain same. For example, if it is 0, it need to be 0 for this to work properly. But even if it is 0 or 1, then the output will be work properly. So we have to change the circuit like that way. So that is what is done in the priority encoder. So if it is done like that, the higher bit, so which bit is the higher, that the output only depend on that thing. So which the output may not confuse even if one or more bit are same. So that is what the advantage that it gave in order to overcome the redundancy with the help of that. So let me mark all things as don't care. So the output may be 1 or 0, the output will remain same. So that is what the application of don't care that we already discussed. Okay, so this is what the priority encoder that it can do. So we can draw a truth table for this one. So how we can draw is we can draw y0. So y0 can be drawn with the help of this kind of truth table. For an example, this is a 3 bit. So if you need to write it for a 4 bit or any kind of things, so we can just draw a truth table and we can solve the things. So here also we can draw. So for an example, here that is as a here it has an 8 variable. So here we can do. So if we have a 4:2 decoder, so for an example, if we are having 4:2 encoder, then we can do. So let me draw one truth table for that. So here, so let me first draw a truth table. So this is enable, and this is I3, I2, I1, and those kind of things. So this is I1, I2, I0. This is Y1 and this is Y2, right? So this is even at 0. This is considered as don't care XXX, and this is 0, 0. This is 1, 1, 1, 1. So this is 0, 0, 0, 1, 0, 0, 1 X, 0, 1 XX, 1 XX, XX. Okay, so this will be 0, 1, 1, 0, 1. Sorry, this is 0. I'm again making the same mistake. This is confusing. The first 0, 0 is confusing. So 0, 0, 1, 1, 0, 1, 1, right? Okay. So let me draw a truth table here. Sorry, K-map here, so that we can solve it. So here we need to find out the two things. What is y0? What is the function of y0 and what is the function of y1? So let me solve. A window, a small edge. We draw this in art class, right? That window. So we are converting this into. Actually, this need to be 4 input, right? So the I1, I2, I3, I4. So I'm again splitting this. Okay, I'm making again. So this is for y1, right? So this is for y2. Okay. Okay. So let me draw it. Okay. So let me take in this order I1, I2, I3, sorry, I0, I1, I2, I3. Any order you can take. I am taking in this order. Okay. So let us draw Y1 here. So this is for Y1. So I am using white color for Y1. So here was 0, 0, 0, 1, 1, 0, 1, 1. I made a mistake here. 1, 1, then only 1, 0. So 0, 0, 0, 1, 1, 1, 1, 0. Right. So what are the case at which the Y1 can be enabled? So here if you see, this is XX, means what are the possibilities can come is the 1, 0, 0 can come, 1, 0, 1 can come, 1, 1, 0 can come, 1, 1, 1 can come. So all these are possible. So considering this, let me mark all the possible things that can come. So here that is 1 XXX, means all the subterms will come below that. So means the below all 8 entries will be enabled. Okay. So from here, this one is already enabled. So these 3 we have to include. These 4 we have to include. So that means 1, 1, 1. This will also become. Okay. So this is how this logic will come. So even you can expand this one. So because we need to add 0 also here, right? So if we add 0 here, here 4 times will come, here 8 times will come. So that is what here. So let me map it. So I'm using red color here. So we can map this together and this together. So if we do it, then y1 can be equal to I2 plus I3. Here you see y1 will be enabled only when I2 and I3 is there. So this is what we are trying to implement in normal decoder itself. But the thing is that when if any of this bit is set to 1 or 0, then that will not work. So in order to avoid that condition, we have built a circuit in this same way. So here if we represent this for y0, so let me take a blue color. So if we represent I1, I0, I1, I2, I3, so this is for y0, right? So y0, this will come as some different values. So let us substitute and find out. So this is 0, 0, 0, 1, 1, 1, 1, 0. So here it is 0, 0, 1, 0, 0, 1. So 0, 1, 1, 1, 1, 0, right? So here the thing is that the 1 will be possible at these two values. So which is 1, 0, 0, x 1. Here 1, all the below 8 terms will come here as we discussed like previously. So here only 2 terms, which is 0, 1 and 3. So both term only come. So this will be 1 and this will be considered as 3. So how we can map here is that, so this 8 can be mapped together and this 2, this 4 can be mapped together. So if we draw the thing, then the thing is that I3 plus I2 dash plus I1. So here we can clearly see it's come directly like this one. But in this case, in the Y1, if you see, sorry, in the Y0, we could see there is some difference. So if we use this kind of logic, then that will act as a priority encoder. So this is priority encoder. Okay. So I hope you can able to see some difference here. So instead of directly writing, so we may directly write this like this. So here we can see which need to be one only when both the input are there, right? So instead of writing like I2 plus I1, so here also we can directly write which is as I1 plus I3. But here if you see, this is an unique number. So only at this input, this output will be 1. So why we have made this is that in order to make this as a priority, even if it is 1 or 0 or 1 and 0, the output will not change. So this is only. So in order to make this consistency, we are choosing the circuit in this way in order to make this as a priority decoder, priority encoder. So this is one of the very important application, guys. So please make a note of it. So they may ask why we need a priority encoder is. So we can say the I3, the output, the code conversion will need to work seamlessly. Whatever the lower bit value, even it is 1 or 0, the code conversion need to work properly. So for that purpose only, we are using the priority encoder. So please make a note of it and you guys can able to do it. So from here, we are concluding our combination circuit. So we have seen all the things like adder, subtractor, universal adder, ripple carry adder, carry look ahead adder, and comparator, mux, demux, like everything, and then encoder, decoder. So we have completed everything. So I hope you guys have enjoyed this lectures. So if you guys understand all the concept, I will be very happy. So please post your observations and comments in the comment section so that I can able to improve it and make it more good for you guys. So please follow this lecture. These will be very much helpful for you guys in your core placements and all the things. So please stay tuned for other lectures. So we will be starting sequential lecture on data converters and also memories. So another 3 more chapters is there. So once that is done, then you can clearly say that you are master in the digital electronics. You can clear gate examination, interview questions, college placements, any kind of things you can do. So with this, I am closing this session. Thank you. Stay tuned, guys.